let x comma tau topological space y comma tau dash be as Dorf space f is a map from x to y, continuous map. Then the claim is that the graph of f, which is the following set C, is closed subset of x cross y, where x cross y has product topology proof. So given f is a map from x to y which is continuous, y is Hausdorff and x is just given to be a topological space. So the topological definition of continuity, what does it give? Gives inverse image of open set is open. We are having what? C is the following set x comma f of x such that x belonging to x. C is a subset of x cross y. This is the Cartesian product of x and y. We wish to show that C is a closed subset in x cross y. So what do we show? So one way to show this thing is that show that its complement is open. So we consider the following set x cross y minus c. Let's call this set as, right, we say T. We show that T is open set in x cross y with respect to product topology. Okay, so if you take any point in T, so maybe say, suppose I have a point R comma S, any point belonging to T, we show that there exists open set in x cross y such that, let's say, such that R comma S is contained in that set and is contained in of course this is a trivial fact. So T, the complementary space we are showing for A. So I have what we are showing is that here is the product space. Suppose this is X cross Y. Here is our C. This is our complementary space. So what is the point is that in this complementary space, if you take any point over here, you'll find that there is an open set which is completely contained in the complementary space. Okay. So for every point, I can find an open set here contained in in the black shaded portion T. So that would prove that C is closed. Okay. To do that, we do the following. So since R comma S belongs to T, which is X cross Y minus C, that clearly implies that R comma S does not belong to C, which is collection of all the set X comma F of X such that X belongs to capital X. This certainly implies S cannot be equal to F of R because it's this kind of in the complementary space. So S cannot be F of R. So S and F of R are distinct points in Y. Y is given to be Hausdorff. So that implies that there exist disjoint neighborhoods maybe say S and so T is used, maybe say V such that S belongs to S and F of R belongs to V, S, V, both subsets of V open and S intersection V is empty set. This is the Hausdorffness of Y what we have used. So what we use is the following fact. So over here F of R is in V. So S belongs to S, and this also implies that R belongs to F inverse of V. S belongs to S and R belongs to F inverse of V. Let's call this set by a name as maybe say U. So this all objects. So S is a subset of Y, but F inverse of V, which is U, is a subset of X. Let's consider the following objects now. So what do we have? We have S cross V as a set. We also have we consider on the left hand side S is a subset of Y. So take U. So we have U cross S and U cross V. Okay, U contains what? R. So R comma S belongs to this set, and R comma F inverse of V. So this is F of R. This belongs to what set? This belongs to U cross V. S and V. So we also have that U cross S intersect with U cross V is clearly what? It's an empty set. Because now let's take any arbitrary point in C. So what happens? Let's write this down. Consider the point Z comma F of Z, which is a point in belonging to where? C. Any point there. Okay, if there is any point in, maybe say X, this implies that it is in C. If you have this point, what are the possibilities that can occur? The possibilities which can occur are that, so if Z does not belong to U, that certainly it implies that Z comma F of Z cannot belong to U cross S, because the first component itself is not there. If Z comma F of Z is there, belongs to U cross V, what does that imply? Z belongs to U, F of, since F inverse of V is U, so Z, so apply F. So this clearly implies that from here itself we can say that F of U is contained in V. So you have Z is in U. What do we have? Is that F of Z belongs to V, and that clearly implies that F of Z cannot belong to S, since V intersection S is empty, or S intersection V, this intersection, it is not cross, S intersection V is empty. Okay. So what do we have? We have over here is that so Z, even if, what are the possibility? So if you look at here, there are two possibilities. Either Z does not belong to U, or the other possibility is Z belongs to U. In both the cases, what we are getting? We are getting the following. Is that Z comma F of Z, the point does not belong to U cross S. Okay, in both the cases. If the first component belongs, then the second component does not belong. If the first component does not belong, then that is in both the cases. So in other words, what we have found out? We have found out that there is an open set which does not contain what? And U cross S is what? U cross S is a set which contains the following point. R belongs to U and this S belongs to capital S. So R comma S was any typical point belonging to T, which is X cross Y minus C. So R comma S is this object. It was any point, and we have found this thing. What does this mean? Since this is also arbitrary point in C, this clearly means the following. U cross S, this set intersect with C is empty set. So this clearly implies that U cross S belongs to where? Is belonging to X cross Y minus C in the complementary space. In other words, U cross S is contained in T. In other words, that so it's an open set in the product topology. U is open set in X, S is an open set in Y. The product topology, so in R comma S was a typical point belonging to T. There exists an open set U cross S such that U cross S is contained in T. So what does this mean? T is an open set. So if T is an open set, its complement. So C is closed set. So hence the proof. If X is taken to be B, Y is taken to be B dash, B and B dash are Banach spaces. Then clearly one can see B is a topological space with respect to norm topology or the metric topology. B dash is also the same. In fact, since every metric space is Hausdorff topological space, so we can consider continuous maps from X to Y. X would be just a topological space and Y would be a Hausdorff space. So the graph, so this is continuous map. Then the graph of, as by previous definition, graph of F is a closed with respect to what topology? Is closed set with respect to the product topology on X cross Y. But what alternatively can be thought of is the following. If B is a metric space, B dash is a metric space, we define a new metric. Suppose B comma D is there and B dash comma D dash is there. Consider the Cartesian product B cross B dash, which is collection of the points U comma V, such that U belongs to B and V belongs to what? B dash. Okay. We have this one. What can be said is that we'll put a metric structure on this thing. Let's say D tilde on B cross B dash as follows. So what is d? D is just the norm. So the distance between x and y would be just norm of x minus y. The d dash of distance between u comma v would be norm of u minus v in, let's say 1 norm. This is a norm on d, the 1 norm on b dash. X and y belonging to b, u and v belonging to b dash. Okay. Let's define the map d tilde. Okay, let's take a point here. Okay, u comma v. So I have just used here u comma v. Let's say just slightly change this thing. R comma s. R comma s, because u is used here for all x, y is in b, and here we just say r comma s. Okay, because abuse of notation would be a problem. If you have this thing, so let's take 2 points here in b comma. Suppose g and h is a point in b cross b dash, and suppose u comma v is also a point in b cross b dash. We define the d tilde distance between the point g comma h comma u comma v. This distance as the following. We say we'll just use as maximum of norm of g minus u comma norm of h minus v, the 1 norm of this thing. Okay. So let's check that indeed d tilde is a metric on the space b cross b dash. If you look at this object, these are any 2 points. This is always non-negative, since norm of g minus u is non-negative and norm of h minus v, 1 norm. This is also non-negative. G and u belong to b. H and v belong to where? B dash. Okay. I have this thing. Okay. Non-negative. If this is this 0, if d tilde of g comma h comma u comma v, this is 0. So the maximum of norm of g minus u comma h minus v, 1 norm, this is 0. Both of them are non-negative. The maximum is 0. This implies that norm of g minus u, this must be 0. And norm of, because it is bounded below by 0, that implies that g is equal to u, 1 norm in b, and h is equal to v in b dash. The first condition is satisfied. The second condition with respect to the symmetry is clearly in the fact that, since if you look at the d tilde g comma h comma u comma v, this is what maximum of, so norm of g minus u comma norm of h minus v, 1 norm, which is the same thing as maximum of u minus g comma norm of v minus h, 1 norm, which is the same thing as maximum of, you can interchange this also, h minus v comma norm of g minus u. So this is just obtaining the interchanging of this thing. This is just rearranging, which is nothing but the detailed u comma v comma g comma h, which is u minus g. So just rub this part. If you look at this thing, this is just this one. This is equal to this thing. So we get that. In fact, this is the case. Let's come to the third property. The third property is the following. D tilde of g comma h comma say u comma v we are considering. There is a, maybe say, let's consider third point, C comma D, where C belongs to B, D comma to B dash. So what do we have? We have that, let's consider another case, term, comma, C comma D. And the third term is what? D tilde, C comma D, comma, U comma V. They have these terms. This is by definition is the maximum of norm of g minus c comma norm of h minus d 1 norm. This is the maximum of norm of c minus u norm of d minus v, the 1 norm. And this is nothing but the maximum of norm of g minus u comma norm of h minus v 1 norm. Now this plus this, what we are claiming is that the maximum of norm of g minus u comma norm of h minus v 1 norm is less than equal to the maximum of g minus c h minus d plus maximum of c minus u d minus v. And let's try to look at this case. Okay. So we'll try to, so this is our claim, what we are trying to prove. Since norm of g minus u in B, these are all the terms in B, G, C, and we say U, and the terms which are H, D, and V belong to B dash, always less than equal to norm of G minus C plus norm of C minus U. And norm of H, this is H minus V, one norm is less than equal to H minus D, one norm, one norm, one norm, one norm. If suppose the maximum of these two terms is this term, and maximum of these two terms is this term, maximum of these two terms is this term, and this term in this case, this term, and that is clearly satisfied. If the maximum is this thing, in the case, if this is this case, and this is this case, and this is this case, then we are also done. Norm of h minus v is less than equal to norm of h minus v plus norm of d minus v, norm of g minus c, and c minus u term. These first terms and so on, they are the maximum. If suppose this is the maximum term, even if this is the maximum term, what would happen? Out of these two terms, suppose this is maximum term, but this itself is less than equal to this thing, and this is less than equal to this thing in the maximum term. So what do we get is that this would be less than equal to this, and suppose this is also small, this is maximum, so that is in that case also. So it is clearly easy to verify using definition of maximum and this one, that this is indeed the case. So all of the properties of metric space, what is required, is satisfied. If that is the case, then what do we have? Is that B cross B dash is a metric space. Is a metric space, and if we consider the set C, which is x comma f of x, okay, this set such that x belongs to B, our and f of x is in B dash, is a map from B to B dash, continuous. So C, this is the claim, is a closed subset of B cross B dash with respect to this metric d tilde. So first of all, note that we'll prove that the metric is equivalent. The metric d tilde gives a topology tau tilde on B cross B dash that is same as product topology on B cross B dash, that is every open set in B cross B dash is open in product topology. This would be a metric topology, so in here this is product topology and vice versa. So let's show that. Take a typical open set or the basis in B cross B dash. So we look at the ball d tilde centered at the point u comma v with radius epsilon. Epsilon is strictly greater than 0. So what is this thing? It's a collection of the point R comma S such that R belongs to B, S belongs to B dash, and the d tilde distance between u comma v and r comma s, that is what strictly less than epsilon. This is in fact r comma s such that r belongs to b, s belongs to b dash, and the maximum of norm of u minus r comma norm of v minus s 1 norm, this is less than epsilon. Okay, this implies that clearly this is the same set as r comma s such that r belongs to b, s belongs to b dash, norm of u minus r, that is less than epsilon, and norm of v minus s, that is less than epsilon, because the maximum is less than epsilon. So if you look at this object, so whatever the maximum is there of these two things, so both of them is less than epsilon. So what we can do is that we can look at the epsilon neighborhood. So consider b d u comma epsilon multiplied by b d. Okay, so that's the dash. Already b is there, ball is there, v comma epsilon. This would be there. This would be this ball. In fact, this ball would have whatever the radius is there around that point. You take the maximum distance, whatever the maximum distance is, at that point you try to draw a ball. So this is the maximum of this one. So this is in fact contained, this ball, as a, if you have this one around this point, suppose this is maximum, so this is the radius, you draw a ball around this thing, it is, sort of looks like this one. So what is easily seen is that this is contained, this ball. This ball is contained in this thing, and this is a typical open set in B cross B dash with respect to the product topology. So if you take, conversely, if you take this one, this set, so this is a ball centered at U with radius epsilon, ball centered at B with radius epsilon, then we can draw a ball, a larger ball, where this set is contained, and so maybe say, suppose this is the set, it looks like only the inside part, which is just a pictorial. Suppose this is some epsilon dash, a typical epsilon. This would be a typical, this one, open set in. So you have the basis. This is just an open ball multiplied by the epsilon. So we are looking at the BD u comma epsilon multiplied by BD dash v comma epsilon dash. So this is some rectangle, and one can easily see that if you take this point and take the distance, so you can certainly draw, this is a finite rectangle, you can draw a larger ball around this thing. So you have to consider it's a finite set, the diameter of the set. Take the diameter of the set as a radius and draw this thing. You can draw certainly the ball which contains this thing. So this is contained, sorry, in the, so this is contained in a ball. around that point. So around that point we have found the radius. So every open set that would be sufficing for u comma epsilon and the epsilon tilde if you want, and v comma epsilon tilde. That would give you that this is in fact every open set in. So as a basis element, we have found that one basis element is contained in this thing. So the product topology is contained in the metric topology, and conversely the metric topology is contained. So if you have a basis element which is contained in the basis element of the other, then you have the reversals of the topologies. So these two topologies are in fact equivalent, or they can be compared to each other, and one is contained in other, so they are the same topology. So they give the same open set. Since we have already shown that it C is a closed set in the product topology, so it is closed here also in B cross B dash. The set C is closed set in product topology, and we have shown that C product topology is the same thing as the metric topology d tilde. Okay. So what does this give? This gives that we have in both the cases that the C is closed in this metric topology on B cross B dash. So if you take a limit point, maybe say of the set C, so U comma V, suppose let's say I comma J belongs to C bar. So if suppose not only C bar, suppose let's say it belongs to it's a limit point C dash, since C bar is C union C dash, it's a limit point. So there exists what? So every neighborhood as a topology, if you look in the product topology, every neighborhood of I comma J intersects C in the point other than I comma J. If with respect to the metric topology, there exists a sequence xn comma txn. This sequence that is converging to I comma J, and because the maximum is there in the consideration, you can easily see that this is what convergence which is happening with respect to what in coordinates also. That is xn converges to I in B, and txn converges to J. So this converges the product topology, this kind of thing I comma J. So the point is that because C is a closed set, what would happen is that I comma J is in the set. So xn converges to I, it's in some element. So this would be, so J is nothing but we will get that J is equal to I'm using T, rather it should be F, sorry. So it should be the J is F of I, pointwise convergence and so on. So what do we get from here is that already the closeness is established with respect to that because of the pointwise convergence. So we can here also we get that coordinate wise convergence, xn converges to I, f of xn converges to J. It's a closed set, so I J must be f of I, and hence what we have shown is that the closed graph theorem, one part of the closed graph theorem, and we'll show the reverse part also. we have seen that if f is a map from b to b dash, continuous, b and b dash, Banach, then graph of f is closed. With respect to the product topology as well as which is the same as the metric topology d tilde, maximum metric on b dash. This rather helps in you can have coordinate wise convergence, and you can prove alternatively here also what we have seen, but we have proved in a more general setting and a topological setting. If you have a map from a topological space to Hausdorff space, and that is the case. Okay. Let's try to prove the closed graph theorem on the converse. The closed graph theorem. So F is a map between Banach spaces. Continuous. B and B dash Banach. Rather, continuous part if and only if, okay. What would reframe this thing? F is just a map, okay. B dash Banach. F is continuous if and only if the graph of F is closed. Okay. So this way done to the proof of the converse. So what we want to prove this way: given the graph of F is closed subset of B cross B dash, which is our set. So we will show that given this thing, will show that in fact this is continuous. So we renorm the space. We consider the space B1, which is equal to B dash, just a subscript, as set, and the one norm, if you take is nothing but norm of x plus norm of fx in this case. Okay. Let's check that this is indeed a norm on B. So consider the following: B, the B1 and B dash. Identity mapping. B is as a set, so you consider the same F which is given. The graph of this is closed in B that is given. Okay. So what do we have is that the identity map from B to B1 to X. Here it is norm X. Here is one norm of X, and norm of X is less than equal to norm X plus norm of f of X, which is one norm. So this identity mapping, so norm of X is less than equal to norm of X 1. So by this it is clearly that if Xn converges to, so if you have a Cauchy sequence in B, that would imply that Xn Cauchy in, so B1 in B, and f of Xn Cauchy in B dash, because this is the definition of the sum. Now what does that mean? Because the graph is closed, And first of all, the space B1, so the space B is given to be what? It's a complete. So xn converges to x. F of xn would converges to some y. It's a Cauchy sequence. Now the graph is closed. So what do we have? Y must be equal to what? Because it is the xn comma fxn, the sequence xn comma fxn, they belong to C. So that is the reason we have that y is equal to f of x. So the identity map, in fact, this map is 1, 1 onto continuous as a map from B to B1. So what do we get? And we have used that the closeness of C also. The identity map is satisfying this thing by the corollary to the open mapping theorem. The inverse is also continuous. Is continuous. Or in fact, this is a homeomorphism. So the B and B1, because it's identity map, they have the same open sets. Okay. Now the function, as a function which was there from f was from B to B dash, f is as just a function from B1 to B dash is also continuous. Why it is easy to see that is that if you look at the one norm, so f of x here is the one norm of x. So if xn converges to x in B1 with respect to the one norm converges to x, then clearly f of xn converges to f of x. Okay. So what do we have is that f is a continuous map from what space? B1 to B dash. I is also continuous map. I inverse is also continuous map. This is I inverse, or rather f is there, so you can have f composed I also. So the composition of two function f composed I is indeed what? They have the same open set. Inverse image of open set is open. B and B1 are homeomorphic spaces, and because it is identity map, I of x is equal to x, they have exactly the same open set. So inverse image of open set is open. So what are the all open sets which are inverted here? They are open in B1, they are open in B. So f composed I, inverse on open set would be the same thing as f inverse of open set on B1. So what does this prove? This proves that f is what? Is a continuous map, not only from B1 to B, but f composed I also is continuous, composition of two continuous function, another way to look at this thing. So which is indeed again f. So f is a continuous map.